Hi apes. Today we're looking at Unit 8, Part 5, which is going to focus on human health and environmental risks. So I want to start off with what are the things in the environment that can cause us harm. We can separate these into three very general categories of biological, chemical, or physical. So biological, most often these are going to be infectious diseases or pathogens. Those are the ones that cause us harm. So most of the time here we're talking about bacteria and viruses. Now a lot of times these bacteria, viruses, or parasites will need a vector, and that is a mechanism to transmit it to humans. Now, one of the most common vectors are mosquitoes. So mosquitoes are one of the biggest vectors in the insect world and transmit things like West Nile virus or malaria. Now, chemical hazards out there, we have several examples that we've already talked about in here. Now, one that you'll focus on in this unit is a group of chemicals that are called POPs, persistent organic pollutants. Now, a lot of the different types in here are industrial chemicals or pesticides. Now, one of the problems with these is that many of them tend to be carcinogens, meaning they cause cancer. Now, another group of chemicals that we've already talked about are heavy metals that are in the environment. And when we're exposed to them, either through our food, through biomagnification, through air pollution, mercury and lead are two big ones that are neurotoxins, so they affect our nervous systems. Now, physical hazards are going to be more things like accidents, natural disasters, storms, things like that. That would be under our physical hazards. So if we take a look at a lot of the main causes of death of people, cardiovascular disease is one of our leading causes of death. Infectious diseases as well. This is more so in developing countries, but also respiratory diseases, cancer, and accidents as well. Now you're going to be diving into our biological forms of harm a little bit by focusing on these diseases that are characterized by the CED. So really focusing on things like plague, malaria, tuberculosis, some of our vector-borne diseases, dysentery and cholera, more of our waterborne diseases. SARS, MERS, you could definitely add COVID to this category now, and back down to a couple more mosquito-borne viruses with Zika and West Nile. So we'll be taking a look at the cause, the effect, and the treatment of these very specific diseases. Now with chemical diseases, we do have some different categories of how we can classify our chemical components. So carcinogens are those that cause cancer. So these are very specific chemicals that are cancer causing. So just to give you some examples of things that might be carcinogens in your world, pesticides, UV radiation, which is why you wear sunscreen, radon that might be coming up from your basement, in your foods, particularly processed foods, some of them will have carcinogens, lifestyle choices, particularly things like smoking, or industry, there are chemicals in paint or medical radiation. And finally, some viruses can also make you more susceptible to cancer. A mutagen is a chemical that might cause a mutation. Now, some mutations will lead to cancer, but not all. A teratogen is a chemical that leads to birth defects. So this is particularly of a concern to pregnant women. Neurotoxins are those that affect the nervous system, things like our mercury and lead that we've talked about. Allergens are chemical toxins in the environment that your body responds to by with itchy eyes or with a cough. And then finally, endocrine disruptors. Your endocrine disruptor is your hormone system. And so there are a lot of chemicals out there that are hormone mimickers. In particular, there's some that mimic estrogen, and that was a big problem with some plastic components of baby bottles a few years back, that they had endocrine disruptors that were released when they were heated. So you're going to be receiving this chart that goes through some of our major chemical toxins. It tells you where they might come from, how they impact you, whether they're carcinogens, neurotoxins, teratogens, or endocrine disruptors, and then the effects. So these are some of the key chemical concerns, so you'll be receiving this as a document. Now, one thing that we worry about toxins in the environment is how they can build up within an individual or within an ecosystem. So bioaccumulation and biomagnification are two vocabulary words that often get a little bit confused. Bioaccumulation, if you notice here, it starts off as a small fish, a medium-sized fish, a little bit bigger, and then a big fish. So this is how a toxin builds up within an individual as they are exposed to it across their lifetime. So this is like a body burden. How much of that chemical are they holding on in their tissues? Heavy metals are something that will build up in our tissues if we're exposed to more and more of them. Now, this is slightly different than biomagnification. If you look down here, there are different levels of our ecosystem, and this is working their way up a food chain. So biomagnification, if you remember, is that as you get higher in your food chain, your concentration of that toxin increases. So it is the increase of a toxin as you move up the food chain. That is a good definition of biomagnification. So increase in, probably in concentration. So increased concentration of a toxin as you move up the food chain. That here you start with very little, and because a fish will only eat a couple of those zooplankton, you don't have a high concentration of that toxin. But this seal is going to eat a lot of these fish, and each of those fish will have that level of that toxin. The polar bear is going to eat several seals, and the seal has a lot of that toxin. So our higher levels of the food chain are going to be much more vulnerable and much more affected by this toxin. And that's different than bioaccumulation, and this is the buildup over the lifetime of an individual. So buildup of a toxin in an individual. So it's just two different ways of looking at how a toxin can persist in an individual. Now, we do have some legislation associated with toxins. One is the Stockholm Convention. And the Stockholm Convention regulates those persistent organic pollutants. It started off by recognizing the dirty dozen, or 12 very particular pesticides that should be banned from world use. It has since expanded to look at more persistent organic pollutants, but the Stockholm Convention focused on these persistent organic pollutants, recognizing that they can have a world impact. So this is more of a world, a global plan. And the Delaney Clause of the Food, Drug, and Cosmetic Act is a U.S. law that states that no cancer-causing agent can be added or detected in food. So it focuses on carcinogens in foods. And really, the key thing here are dyes and pesticide residues. There are a lot of dyes that have shown to be carcinogens, particularly red food color dyes. And also knowing that pesticides are often carcinogens, but we commonly use them on our foods, recognizing that there's certain levels of pesticides that need to be managed and make sure you do not cross a threshold that would put it in more of the risky category. Now, speaking along those lines, there is always going to be some level of danger in the food you eat, particularly with pesticides. So toxicology is the study of these chemical risks. And the key thing that is the most important is that looking at the dose of the chemical that you're taking in. A small amount of a toxic chemical may not have a big impact, but a large amount is. And everything in the world can be poisonous. Even water can be poisonous if you take too much of it. So really one of the most important things to think about with toxicology is knowing what the dose that you're taking is. And also extrapolating that dose to your weight. A lot of times what we'll look at doses is is milligrams per kilogram. So 10 milligrams of a medicine for you may not be as effective as 10 milligrams of a medicine for me, because we could be different sizes. So recognizing that dose has to be calibrated per your size, how it's spread out in your body. Another thing to look at with toxicology is how often are you exposed to this toxin? Is it a one-time thing, or is it a gradual background exposure for many years? That's another important thing. Your genetic makeup. Remember that everyone has that range of tolerance of toxin exposure, of exposure to different types of abiotic factors, that some are going to be very sensitive to it, some will be moderate, and some will be very tolerant. And then we can take a look at both response and dose in terms of acute or chronic. An acute dose or acute response is something that is done in the short term. So this tends to be a large amount of dose over a very short period of time, whereas chronic is long term. So spread out over a very long period of time. Now, a dose response curve, this is what I was getting at with how resistant people are to a toxin, that in any given population, you do have some that will show very mild symptoms to exposure to the same dose because of their genetic makeup, maybe because of the frequency they're exposed to it. The majority will fall into an average response, and then some will be very, very sensitive. This could be tied to allergies, could just be tied to genetics. So to any toxin, you're going to see a range of responses. No two people will respond in exactly the same way. Now, another way to look at a dose response curve is by taking a look at the dose, and this actually should probably be dose in milligrams per kilogram. And we take a look at dose response. So this is how many people responded to this dose. So one very common measurement that we use is a dose that's called LD50. And what this refers to is a lethal dose for 50% of the population. And the 50% is a general baseline data. You can actually use any number that you want, but LD50 is the commonly used level. And so what you do here is you find where 50% is on your y-axis, you cross over, and you drop down, and I see that probably my LD50 is about 24 in this case. So what this means is that for this particular toxin, 24 milligrams per kilogram would kill 50% of the test population. So as you're testing out medicines or products, we'll often do this test on rats to determine the LD50 for a rat population and extrapolate that out to humans. So this is to determine how lethal something is. That if you have a curve that's 24 milligrams per kilogram, that is going to be much safer than a curve that, say, looks like this, where the LD50 is closer to 5. So this is a good comparison to see how dangerous a toxin might be. So you'll have these different LD50 curves for different toxins, chemicals. Now, another important level here is that you see that there is a point that there is no lethal effect, and that point is the threshold. So the threshold, what we refer to that as, is it's the maximum dose that has no response, or the maximum safe dose. That in this example here, you could take 10 milligrams per kilogram and have no lethal effects. And that would be a safe dose to take. So this is something that they might use to develop safe doses for over-the-counter medicine. How high can you go without having any lethal or toxic effects? Now, LD50 is a very common curve, but you also might see this in the context of a TD curve or a toxic dose curve. And so all that means is that this level, this shows toxic effects, nausea, discomfort, headaches, blurry vision. So those could be some toxic effects, and you might find a toxic dose curve for 50%. So we're going to do some practice with this in class. So just make sure you ask any kinds of questions you have about using this LD50 curve and determining either the threshold or the dose response for it.